is recording, and we are here. Okay, so for those who gave me homework, what did somebody do? Declare a holiday today? Good.
I think I have someone online.
What's that?
I have someone on the Blackboard, I think.
Okay, I'll get it and grade it. These are just ones I collected the other day. These are actually pretty damn easy to grade. Difficult one was that one. Close, but you didn't know what to do with a bending moment, did you?
No, I tried calculating it a few different ways and could not work it out.
It actually's got a unique plot in life.
2% was very hard, right? 2 of them was really hard.
All right. So I know one thing for sure. I will not give you a cantilever problem on Friday. Oh, goody, I brought all kinds of stuff in from the other lab. I'm not wearing my safety glasses today, so that means I left them someplace. All right. Those I gave you stuff back, take a look at the one problem and make sure you understand what went where and why. It's got a unique little twist in it, but nothing that's horribly detrimental. All right, let's see here. So, you see, Fidelo's taken over your role of, camouflage. Black hoodie, black jacket, black mask. Although he's wearing blue with a white mask today, so. Okay, so let's go do one of these problems that I was talking about at the end of class. Monday? Yeah. All right, so we have a beam that looks like this. You guys can't see anything. Sorry. How long are you going to wait for me?
Before you start talking.
Okay, I'll give you a chance to draw that. What we're going to look for is so someone took a box beam, we'll call it for the moment, decided to hang two things off it that are eccentrically loaded. Okay. Mark it down, November 3rd. We have snow.
Tug Hill's already gotten like 3 inches.
Who did?
Tug Hill.
Okay, everybody good? Drawing? All right. So we're going to take that force down through here to draw our lines and stuff. But no, I'm sorry. What am I thinking? We're going to draw it back over to this point over here. And think of it this way, okay? I can translate that this way, and that's still there. But in order to do that, what do I get here? Is I wind up with a moment that goes along with that, okay? Everybody see that? Okay. So the interesting part about this is when we get done with the shear diagram, it's not going to look like the beam anymore. But even when I do the free body diagram, it's going to look like this. Okay, so we got the reaction at A. We got the reaction at B, and I'm going to give you the reactions here so we don't have to go calculate them. But I'm going to do here at C, we're going to do Fe, and then here at D, we're going to do FF, but we also get a moment here, all right, and moment at E, and then we got another moment here at F, okay? And we've dealt with these moments before when you get to it. Does the moment affect the shear diagram? I need to be clear, Frank.
No.
Loge? I don't need blue mask. I thought you did. Blue hoodie, blue mask one day?
Oh. Isn't the moment diagram that addresses the shear?
The moment on the 3-body diagram does not affect the shear, but we are going to need that moment when we do the moment diagram. Right? Okay. All right, so we can move down through here. Now that we got that force there, or we got things sorted out, we can go here. All right, so I'm going to give you reactions at A. So a reaction at A is equal to 2 kilonewtons, and the reaction at B is equal to 6. Okay, you guys should by now be able to figure that out without any help from me, the world, the universe, or your neighbor, right? Anybody not good at statics yet? Cool. All right.
That's the question.
Yeah.
So, on the top diagram, where you have the force in the point down, you said yesterday that the force acts straight down to where it is.
Well, it wants to push down through there, but when we do the moment, we can actually translate it to the left.
Okay.
That's what I was trying to do. I did it right. But without that moment in there, we can't. Everybody good so far? Good question, and thank you for. All right, so what's the shear diagram going to look like at A? Oh, so let me do this too. I might as well get. Well, that wasn't very nice of me to draw that in the wrong place. So we got A, C, D, and B, and that's my shear, and it's going to be in newtons. Okay, so that's 0. Where does our A go? Go for it, Montana. Up 2. Okay. Then where does it stay? And at C, what's it do? Oh, I guess we could put these in here. So that's 4 kilonewtons. Okay. Down to -2. Okay. And then it's going to go straight over until I get to the next one. And over, and if the world's a happy place, we did all that. right? Anybody lost, confused there? And those are the equations you're going to use for shear, right?
Real numbers.
Everybody good? Val, you okay? Explain what? You want me to explain? Okay. All right, so the reaction at A has to go vertical to 2 kilonewtons. All right, so that's 2 kilonewtons, and this one's 6 at RA and RB. So we go up 2. We hold steady all the way across there until the next force that acts on it. And that's the FE that we moved over from here that way. Okay? So we use that going straight down. All right. And then we go, so let's call this one FE primed. Okay? That goes down to -2 because it was a 4. Okay, so from +2 down -4 will leave us at a -2. That stays steady until we get into the F sub F, which we translated from this location back over to D, and we force that down. Okay, and then we go back over and hit the reaction at B, and it goes back to 0. Okay. The only thing that's different in this problem is the fact that I use the moment to allow me to translate those forces back over something solid. Okay. So literally, when I got, all right, I'm doing that yardstick. I don't know if I'm doing that yardstick. It goes away. Yeah. That's right. So if I take this, Justin, you're going to be my force. Okay? I'm at, let's take a look at the one at C going over to E. Okay? So Justin's going to be force E pulling down. And I'm going to be C here. Go ahead. So in order to do that, in order to translate that force from here to here, I can move that force, but I also need a moment to go with it. Okay? So I do that by taking the force he applies to that times the distance that I got to travel. Okay? Very good? Anybody unclear? Okay. Thank you. All right. So, cool beans. Moment diagram. All right, so let's draw the line there. Moment, it's going to be kilonewton meters, and we know that's 0. So the moment at A will be what? Zero. Okay. The moment at C And here's an interesting thing. So I want to go back here to shrink this down a bit. So what do I got in here to play with? So I'm doing the moment at C now. What's it going to do? So if I take the area here and play with the area for a minute, okay? So I got 2 times 1 meter, right? So it's 2 at C minus, just before I hit C, right? Then what's going to happen when I do ME? Oh, we should have calculated that. Sorry, my fault. The ME moment's going to cause it to rise, right? Okay. Let's go back and calculate ME before I forget to do it. It will really make life confusing. So the moment at E due to so this turns out to be 4 kilonewtons meters. Okay, so we know this is 4 kilonewton meters. And the one at F will be 4 kilonewtons times 0.5 meters, because that's as far as I'm moving that one over. So we wind up with 2 kilonewton meters. Okay, and that's what balances that system out. Cool. All right, so when I'm doing the moment down here at C, I probably want to do the C minus bit first, because I'm going to look at V of A times 1 meter, 1 meter. Okay, so 2 kilonewtons times 1 meter is 2 kilonewton meters. Okay, but M at C, actually C plus now, just past that, is really going to be the MC minus plus my ME now. Okay, so 2 kilonewton meters. That doesn't look like an M. Plus 4 kilonewton meters. And that'll be equal to 6 kilonewton meters, which means I'm going up to here. Okay? Everybody following? All right, the next one we want is D at just before D, because we got that other moment out there causing us headaches, right? So the moment of D minus will be equal to MC plus the force of F times our 1 meter again. Actually, I'm going to move some numbers down here. So 1 meter, 1 meter, and then we know there's a line here that's 0.5 and 0.5 meters. Okay. All right, so we're going to do that at 1 meter, and that'll be 6 kilonewton meters minus are 4 kilonewtons times the 1 meter, right? F of F was 4, yes. And that makes us 2 kilonewton meters. Did I do that right? What did I do wrong? No, I did that wrong. Sorry, I'm jumping ahead to D plus. Plus V D, no, VC times 1 meter. So the 6 kilonewton meters minus 2 kilonewton times 1 meter. And that should be 4 kilonewtons meters. Sorry, curiosity's got the best of me. Who the hell is trying to get all these Teams messages out at once? Probably all panicking. It's snowing. Good thing we don't live in Antarctica.
Fun drive home. Everybody forgets how to drive.
You don't drive, you have to fly home.
Okay, I can do 90.
You actually have to get an airplane that comes 3 times in the middle of their summer and fly out. Otherwise, if you're there after when their fall hits, you're there until spring.
Yeah.
Not many people leave Antarctica in the middle of it. All right, so everybody good there? So literally, let's put some numbers here. So we got 6 there, we got 4 there, and we're 2 there. Okay. All right, now let's do the MD plus, which will be MD minus plus the moment of F. Did I get the force? Yeah, I did. All right. So we're actually 4 kilonewton meters minus the 2. By the way, somewhere in here we forgot to keep track of our sign convention. So which way did I put those things? You're swinging this way, right? Yes. All right, so that leaves us with 2 kilonewton meters as the answer there. No, that's not what I want.
I think you messed up.
I think I did too. No, I think I messed up down here. I think this one's positive, and I think I just drew this line in the arrow in the wrong place. So it should go to 6, drop down 2. At 4, we drop down, we got to go up 6 because of the 2. Which way do I want to draw this arrow? I want to draw this thing based on what I assumed up here. The arrow is there. So I know it's got to go positive because if I take a look at the shear diagram for this section right here, it's minus 6 times 1. So I got to wind up with a positive 6 at the moment here. So I got my sign conventions wrong on that moment. So I want to draw it like that. And that makes that positive. And then we go to 6. Because it'd be a negative moment here. All right. My head is not in this. Why am I not seeing it? Oh, we didn't draw that. Let's just finish the problem and I'll go back and sort out the signs. So the moment at B is the moment at D plus minus the reaction at B times 1 meter. So 6 kilonewton meters no, let's do that. Minus 6 kilonewtons times the 1 meter will take us to 0. All right, now where did I mess up my sign conventions here? Because I wasn't diligent enough to keep track of them as I was going down through here. So starting at point A, and C's going over. M is 0, don't really care. Positive this. So it would be this. Yeah, so there should be this all the way down. But then I draw them up here backwards. Cool. I messed that up someplace on their sign. Anybody see it? The little thing to the right is my diagram for MC. And E, MC plus, that's be positive. I think I did my signs up top wrong. right here. Ah. Yep, here's the proof, I think. So that's going to try and bend 4 kilonewtons down that way. So in order to counterbalance that, I need a moment out here that does this. Then we can translate here so we're balanced. Yeah, I drew those in the wrong place at the beginning. Everybody okay? Maybe. Carter, stress level on that one? The deer in the headlight look. That's like that 3-point deer I saw this morning on the roadway. It came around the corner and it literally climbed the rock cliff. It's like, thank you, and why the hell were you standing there in the first place? Like, that's that look. I'm glad I didn't decide to walk off the road. You good? Okay. All right, so the reason we do these goofy things like this is because someone's always trying to hang things on stuff, okay? And you gotta fasten it someplace, so you gotta put it back. It'd be nice if the force was actually on F and E. Yeah, it would be nice. But the odds of somebody doing something nice to you like that, never gonna happen. Okay? Cool part is someday when you get to design parts, try not to do that crap. All right? I always think of it as someone decided to put a coat hanger on, or a coat hook on the side of a beam. Yeah, okay, great. The coat hook's this tall, and that's where the stuff's getting hung. So it's actually creating that moment. Okay? Cool. All right. Now, let's have a little chat about a different style of beam here. How about something that's like this? Oh, we never did find the stress in that problem, did we? I'll let you guys do that. Sorry. And let's make this all fastened down. Actually, let's do that a little better than that. So we got it sitting on a piece of metal. Comes an iceberg in the middle of nowhere. What do we got? Is that a beam? Henry? Does that look like a beam? Okay. It is similar to what we're just looking at. Okay. So if I draw the free body diagram for this thing, it's going to look like this, right? And I have this force here. But now if I decide to translate that over to here, okay, then I got to have a moment that goes with it, right? So let's give this distance, we'll be exaggerating. Let's make it 3 meters. Okay. Let's make it 1 meter wide and 0.2 meters high. Okay, and that'll be consistent. So this is 0.2 meters here, and we're 1 meter down in here. Okay, now the top half acts like a beam. What about the other piece of metal that's sitting down there on the little iceberg that's sitting out in the middle of nowhere? Is there stress there? There is stress there. Okay. So there may be times where you're trying to figure out what the stress is right there. Okay. We'll call that A for a minute. So now what happens? Well, we're interested there because this is where it may fail. Okay? And we want to know what it's going to do. So here's how this is actually working. So being attached to the piece here, right? I push down on that end. It's going to do what to the vertical piece here? Going to pull it up, right? So there's stress there too. Now what happens? So I bend bending moment. Okay. So my stress equation for the bending is 3 little letters, 2 on top, 1 on the bottom. Stress is equal to MC over I. Okay. But now what happened back here? So as it's pulling this up, what's happening to the stress in the vertical portion? Way back in the beginning of the semester. Do you remember? No. Montana? Henry? You're going to hate yourself when I tell you. Frank? Nothing she explained? Okay. So you're going to hate yourself. Very first stress equation I gave you was what? Sigma is equal to something over something. Force over area. Okay? So, can you imagine this bending this piece, okay? And then as it's doing that, it's going to try to pull that piece off the iceberg, right? So now what do we get when we're talking about the stress back here at A? We got a bending force, okay? And we got the axial force acting on this, okay? This is what's classified as an essentially loaded problem. It's like the one I just kind of gave you, but that was just a pure bending, okay? C-clamps are notorious for this thing. Okay? C-clamp has a big C, right? It's got a screw that goes up and it clamps at the plate at the top, okay? But as it does that, it's actually going to push that plate upward as you tighten that down to hold the part, okay? The back side of that C-clamp is in bending, but it's also got some axial loading on it, okay? So we have to account for all that. So it's really kind of getting into the point now where sigma is equal to F over A plus or minus MC over I. Okay? And that's where we're heading next. Okay? Make sense? Alright. So a little tidbit of where we are now. So November 3rd, yeah, it's snowing outside. We got about 3 weeks to go. Okay? The next topic I'm going to hit you guys with is compound loading. Bending and axial loads together. Okay? And then, to find those stresses, what's the famous project that you have to do, Frank, for these things, compound stresses? You don't remember?
She didn't give us project.
Moore's circle.
Oh, I should like that.
Okay? We're going to do Moore's circle from now until the end. Okay? Madness when we method. Although some days I'm sure I'm mad. I don't know about you folks, but I'm ready for the semester to end. Okay, we'll see you on Friday. Oh, you guys still comfortable with the test on Friday, or you want me to hold off on it? We can always do it next week. It's not like.
Get over for Band-Aid.
Yeah, I mean, if we're gonna keep moving on, maybe we'll do it all.
Why it's fresh in your mind? Okay. So in the morning, the first hour we'll work on these things, and in the second hour we'll do that little test. And I do mean little. It's just one problem, and cool. Have a good one.